will set you up to do rigid body motion. So this is not rigid body motion yet, not the dynamics yet, but just the basics to get to applying F equals ma when things are rotating. So a brief review. So for any rigid body, there's something called center of mass. This is the point at which you can think where all the mass is actually concentrated. You can take a body which has uniform mass distribution. It's got finite shape, and reduce the for using F equals ma. You can think of all the mass being acting or centered at a particular point, and that point is called the center of mass. I'm not going to define it in terms of words, but I'm just going to show you the formula, and the book will have explanation about how to define it. So if you want to find the center of mass, you need to take the summation of mass times distance divided by the total mass. So what do I mean by this? Well, so this applies to either a simple shape like a circle would have a different center of mass than a rectangle, or a sphere, and so on. So what we'll do is we will be giving you pretty much know what the center of mass of simple shapes are, right? For example, for a circle, it's in the middle, assuming that the mass distribution is uniform. For a rectangle, it's again in the middle. What we are interested here is trying to find the center of mass of composite bodies like such. Okay, so if you're given a geometry which consists of two squares, and I ask you to find the center of mass of the composite bodies, two bodies, where we know the center of mass of this square is right in the middle, the center of mass of this one is right in the middle, but where is the center of mass of this composite body? So what will help you do that is those formulas. So if this is m1, this is m2, this is x1, y1, where x1, y1 is the center of mass defined relative to the origin which I've shown there, and then x2, y2 is this. Then in order to find the center of mass, what you'll do is you just apply x prime, x bar is equal to m1 x1 plus m2 x2 divided by m1 plus m2, and y bar is m1 y1 plus m2 y2 divided by m1 plus m2. X1 and y1 is the center of mass. So for example, of the first one, for example, if I told you that the sides of this square are 1 and 1, then x1 would be half along x-axis, and y1 would be half along y-axis. So if I mean make it clear this way. This is y1. This is x1. Okay, the second thing you want to know is as important as inertia or moment of inertia.
Also, real quick, is x2 from the origin, or is it from the center from the second block?
Good question. It is from the origin.
Okay.
This is x2. This is y2. So the moment of inertia is something which I believe you've learned how to compute in calculus, right? What it physically means is let me just write the formula. If you want to find the inertia of a body, then you need to take a small element at a distance r from the axis along which it rotates, or the axis which you are going to find the inertia, and then multiply the mass and take the integral over the mass. I'm not expecting you to brush up through that and do an integral. It actually boils down to, depending on the body, if it's a plane body, then it's a double integral. If it's a three-dimensional body, it's a triple integral. Not expecting you to know that. What inertia is physically is it's the tendency of a body to oppose rotary motion. Just like mass is the tendency of a body to resist linear motion, the analogous part in the rotational world is the moment of inertia. So we will be giving you the inertias. We are not expecting you to remember them. Few inertia which are important are, which basically come again and again in the class, are the inertia for a cylinder about, okay, by the way, the inertia is defined about an axis, okay. So in this case, for example, there is the axis z, which is along the length of the cylinder, and x and y is along the circle. Most of the time, Iz is half mr square, and Ix, Iy is different, right? So most of the time, we'll be looking at cylinders which roll, which means that we need to find Iz, and that's one formula which we'll be using again and again. The other one which will be coming again and again is this one, and then the ring is important, and then slender rod is important when we talk about pendulums. This is important. I think disc, yeah, sometimes disc is the same as the cylinder. That's important. Nevertheless, you do not have to remember, as I said, we will not give you this table in the formula sheet, but for the specific problem, we will give you the formula, so don't worry about it. At the most, what you might have to do is we might give you Ix, Iy, and Iz, and you might have to figure out which of those inertias you have to use to solve the problem. Okay. Okay, the last thing I want to say before I go to problems is what is known as the parallel axis theorem, and this is two things: parallel axis theorem and radius of gyration. So parallel axis theorem is a way of computing the inertia about a parallel axis, and I'll tell you what I mean by that. Parallel axis theorem. So given a rigid body and you know the inertia about the center of mass, okay, so center of mass is usually denoted this way. So for example, for a cylinder about Iz, the center of mass is mass times length square, mr square divided by 2. You want to know the inertia about a different axis. Let's call that IO. So the table will give you Ig. The question is, how do you find IO? There's a simple formula which relates to IO is Ig plus mass times distance squared. The distance is the distance from the axis which you are trying to find the inertia about, which in this case is the right axis. So that's the d, the distance in the two axes, and you just take the mass of the body and multiply with d squared to get, and add it with Ig to get the IO. So I'll give you Ig from the table, you'll get Ig. You need to find IO. This is how you do it. The last thing before we get to problems is radius of gyration. So what you're given is, typically in a problem, the radius of gyration is so and so. So if you're given the radius of gyration, you only have to take the mass and multiply with k square, which is the radius of gyration, and to get the inertia. You do not have to look at the table. So what is the radius of gyration? It is the yeah. So I should write k here. The mass is assumed to be concentrated over a ring of radius k. So what it means is, if you're given a random body like this, you try to find, and it has its own IG, it's given to you, you try to find in how can you you try to take a rigid body which has a shape. It could be a funky shape, or it could be a cylinder, whatever you have, and try to think of reducing that figure into a ring of radius k. And that particular, so you can, for calculation purposes, you take this body and reduce it to a ring of radius k. In that case, the radius of gyration. It's a way of taking any shape you have and reducing it to a ring of radius k. So how do you get k? Well, you know Ig, it's given to you from the, it could be from the table or something you compute. Then you just find k equals I g divided by m, and then you take the square root. This comes from this formula. So we will not tell you to find, well, we might tell you to find k. Sometimes we'll give you Ig and you will find k. Or we'll give you k and you'll have to find Ig. Okay. So if it's still not clear, I will not be doing a problem on this, but it will be clear once you solve problems. You'll be given k, you have to find Ig. That's all. It's as simple as that. You do not have to look to any table. So let's get started with problems. Yeah? Question? It's not an approximation. It is trying to take something which is funky looking or regular and trying to reduce it to a ring of radius k. So you can take any shape and boil it down to a ring. So there's an equivalence between those two. As long as you have the right k, you can think of any shape as consisting of a ring. Every shape is boiled down to a ring. Now the radius of the ring determines the inertia. So you're not changing the inertia, just that you're trying to interpret any shape as a ring of radius k. That's what radius of gyration helps you to do. Okay, so here is a problem on moment of inertia. Okay, determine the moment of inertia about an axis perpendicular to the page and passing through the pin O. The thin plate has a hole in its center. Its thickness is 50 mm. So the thickness, by thickness, is something you cannot see in a top view, but it's basically the thickness of this disc is going in the plane of the paper. And the material has density of 50 kg per meter square. So you're told to find the inertia about O. O is the pin joint right on top, and the axis is actually coming out of the plane. So think of, this is the axis. Okay.
Is this perpendicular to the
Yes. This is the page,
okay.
and that's perpendicular to the page.
Oh, okay.
So it's right there. Pointing out. Okay, now if this was a regular shape, if there was no hole in it, right, it was just a regular shape, then it's very easy. You go to the table, Yeah, you go to the table and find out what shape it looks like. Well, it looks like this shape. Right? The thin plate. You want to find inertia about this point. So you know the inertia about V. So what you can do is you can use this formula. In this case, I believe A is equal to VI squared. So A equals V, so you can find IVZ. But this IZ is about this axis. You want to find the inertia about the tip. So you can use the parallel axis theorem to find inertia about the tip. However, the issue is that this is not just a square, there's a hole in it. Right? So in this case, it's a composite body. So the way you analyze such a system is by breaking it down into two shapes. So one shape is the square, another shape is the circle. I find the inertia of the square using the method I just described. I find the inertia of the circle using a similar method, and then subtract the two out, and then I'll get what I want. So in words, this is, in pictures, this is how you go about doing this.
So you subtracted the first circle in each.
Yes. So see if this makes sense. This is what you're interested in. About O. I'll find the inertia of this shape, which is the square, about O. Then I'll find the inertia of the hole about the same point O, and I'll just subtract the two. So it's something called superposition, which is you can think of the effect of when you want to find inertia, it's linear in how you compose the shapes. So you can actually subtract the things out and get the answer. In fact, I think I do it two ways. Yeah. So it's linear, so you can do this. The harder way to do this is use your knowledge in calculus, integration, double integral, and then actually do the triple integral. You'll have to integrate from there to here and go through this system. Okay, let's try to find the inertia of, I'll call this 1, 2, I'll call this shape 1, I'll call this shape 2. So I'm going to find IO about, so IO means the inertia about point O for the composite shape. I'm going to find the inertia about O for shape 1, and I'm going to find the inertia about O for shape 2. And as long as I have all this, as long as I can compute this and this, I found what I'm interested in, which is IO of shape 1 and 2. So let's try to find IO1. So IO1 is the inertia of O, but I do not know the inertia about O because the table will only give me inertia about G, the center of mass. So I need to use the parallel axis theorem. IG plus, I would need to find the distance from O to G plus mass times distance squared. So to show this over here, I need to find this distance. So you can see that this distance is half of this distance. So this distance is what? If this is 0.4 and this is 90 degrees and this is 1.4, then this distance is going to be, from Pythagoras theorem, it's 1.4 squared plus 1.4 squared is the square root of the sum, right? So it's going to be, it's actually 1.4 square root of 2. So this distance is going to be 0.7 square root of 2, half the diagonal distance. So I'm finding the diagonal of the square and then taking half the distance. So what I have here is IG is 50, the density, times the thickness, which is 0.05, times the length, of the sides, 1.4 times 1.4. So density times thickness times A times A times the, I got to go back and see the formula for so the formula is 1/12 m a square plus b square. If I put a equals b, I get m a square plus a square, so that's going to be 1/6 m a square, right? So let me go back and then right here 1.4 square divided by 6 plus mass, which is the same thing as here, so 50 times 0.05 times 1.4 times 1.4 times d square, so d is 0.7 times square root 2 square. So this comes out to be it's 6.4. Okay, the next thing I need to do is find the inertia of the circle about point O. Again, I do the same thing. I find the inertia of, yeah, good question. So it's, let's see, so it's in SI units. It has units of mass times distance squared. So mass is in kgs, the distance is in meters, so it's kg meter square. So inertia of the circle is Ig of 2 plus mass times, well, I should be careful here. This is mass of the square and this is the mass of the circle times d square. Where d is the same thing, it's the same distance. That's d. So if I want to find the inertia of the circle, I need to find the inertia about the axis which sticks out of the plane, right? Because once I know that inertia about Ig, I can then use parallel axis theorem. I know Ig and IO, and I know the distance. So again, I go to the table, try to look for a shape. So I think the thin circular disc qualifies, right? So I need to find the inertia about Z. It's half mr square. How it turns out actually that they've actually given you what I'm after. They've also given you I about Z prime. You don't quite need it, but if you wanted it, you can use IG to use about this axis. So here they're giving you extension. Anyway, so let's use this. It's half mr square, inertia about of the circle about an axis which comes out of the plane. So I'm going to use half mr square. Half times mass. Okay, the mass is 50 for the density times the thickness is 0.05 times the area of the circle, which is pi r square. Pi times r is, so radius is 0.15 square divided by 2. Sorry, I already have the 2, my bad. I already wrote the 2 here, plus the mass again, 50 times 0.05 times pi times 0.15 square. So this is rho times thickness times area, or pi r square. Am I forgetting something? I think I am forgetting. Okay, this is half m r square plus m p square. So I'm forgetting, this is just the area, so I need to multiply this with r square, which is 0.15 square. So I need, this is the mass, that's the half, okay, plus the same thing, mass, so 50 times 0.05 times pi times 0.15 square times the distance is 0.7 square root 2 square. Okay, all that gives me 0.175. So the net inertia is 6.4 minus 0.175, which is equal to 6.23 kg meter square. Okay. The pendulum consists of a 3 kg slender rod, so this is 3 kilograms, and the 5 kg thin plate. Determine the location y of the center of mass g of the pendulum, then calculate the moment of inertia about an axis perpendicular to the page and passing through g. So two things, you got to find the center of mass, right? You know the center of mass of the rod, right? It's in the middle of the rod and for this thin plate, but you need to find the center of mass of the composite thing. Once you find the center of mass, you need to find the inertia about g. So I think I have just enough time to finish the first part. Let's try to find the center of mass. Now, x is not very interesting, right? There's an x center of mass and a y center of mass. The x center of mass is clearly over here, right, along in the rod, because the body is symmetric. What is more interesting is y. So the y center of mass is m1 y1 plus m2 y2 divided by m1 plus m2. Where I need to set up y1 and y2 based on some origin. So in this case, since this is O, I'm just going to assume that this is my origin, this is my positive y direction. So let's assume that the first mass is, let's call this m1, call this m2. So m1 is 3. The center of mass of the first body is, where's the center of mass from the origin? The rod is 2 meters, so it's going to be 1 meter plus the mass of the second body times the distance of the center of mass, which is about here, from the origin. Okay, it's not from some random place, from the origin. So what's that distance? So 2 meters plus half of 0.5, right? So 2.125. 2.25, sorry. This is 2 plus 0.5 divided by 2. Divided by 3 plus 5, and what you get is 1.78 meters. Okay, looks like I still have time. Let me just try to set up the second part. So I found y prime. I need to find I, G for the composite system. So I'm going to draw this in this way so that's much easier to understand. This is 1 and this is 2. This is where G is. So IG12 is equal to this is where G is. So I need to find IG about 1, where G is this point now, not its center of mass. G is again center of mass of the composite section. So as long as I find the inertia of the plate about this point and inertia of the rod about that point, I can then sum the two to find the inertia of 1, 2. So what I need to do is, in order to find inertia of G1, okay, that is about this point. I do not have the value for the inertia about this point. What I do know is the inertia about the center of mass, which is of this particular rod, which is about here. So I find the inertia of the center of mass using the table. Then I use the parallel axis theorem to find the inertia about this point. That gives me this. For this, I know the inertia about the center of mass from the table I showed you some time back. Then I can find the inertia